Hello everybody. Today we're going to be looking at double-slit interference. This is one of the really cool things I think when we do waves. Whether it has super practical uses right now is maybe debatable. If you study optics, you might use this. If you study astronomy, you might use this. Astrophysics, one of those options. So there's chances that you'd use it later on, but in reality, it's just a really neat thing because it has several things that down the line are going to be significant as far as our understanding of physics. All right, so let's go ahead and have a glance. Okay, so double-slit interference. This is what it looks like, right? You've got some light. Usually this is going to be laser light, but as long as it is coherent light that is coming through our double slit, then we're good. That's all that we need. Okay, now what does that mean, coherent? Coherent means that the light is in phase with each other, right? It means that the light is doing the same thing at the same time. Okay, so for simplicity's sake, we can say when the light going through one slit is at a crest, then the one at the other slit is also a crest. When the light going through the first slit is a trough, the other one is also going through a trough, right? And so they're doing the same thing at the same time. And the coherent light, really the main thing is that all of the light coming out has to be the same frequency. So it's monochromatic, which actually means one color, or that the frequency is the same for all the light. Okay? Now, what I want us to do is look at what's going to happen if the frequency is the same for all the light. Okay, so we're going to zoom in a little bit here. All right, so what's going to happen, right? We are going to have light coming through here, and we're going to have light coming through here, right? Now, it should be obvious that at some point right in the middle, right, that this wave, the light coming through here, and the light coming through there, because it's right in the middle, right, whatever's happening to this wave up here is also happening to that wave. They're doing exactly the same thing. And because they're traveling exactly the same distance, then when they arrive at the wall, if the top wave is on a crest, then the bottom wave is on a crest. If the top wave is on a trough, the bottom wave is on a trough, right, when they arrive at the wall. Okay, so it really doesn't matter exactly what's happening here. What matters is that they're doing the same thing. And because they're doing the same thing, then if they travel the same distance, because they're traveling the same speed, then when they get here, well, they're doing the same thing. So if they're both at a crest at the same time, and they're both at a trough at the same time, then we're getting superposition, right? And if we have superposition, then the amplitude is double of what it used to be, right? If the amplitude is double of what it used to be, then it's going to be more intense. It's going to be brighter than it used to be. And so what's going to happen is we're actually going to get a bright spot right here on the wall, right in the middle, okay? Now, this is understandable. I mean, right? They're going the same distance. We're getting exactly the same thing. But what happens if I'm doing light that's slightly in a different direction, right? What if this light is going in this direction, right? And then some of the light, now obviously light is going in all directions, right? It's diffracting, it's spreading out. We know that the light spreads out as it leaves, right? So we do have light waves going in all directions, okay? But what if the light going from here travels a certain distance, and the light from here also goes to that same position? Which one of those is longer? Hopefully you recognize that the one down here on the bottom is a longer distance, right? The one on the top is shorter, okay? So the top one is shorter, the bottom one is longer. Now if that's the case, then we have right here what's called a path difference. Okay, now this path difference, sometimes it's shown by a lambda, but it could be any number of things. Sometimes it's shown by a d. The variable isn't really important. What is important is that it's the path difference, right? So the bottom path is longer than the top one. Now, remember, we said that if they went the same distance, this red one here, when they went the same distance and ended up at the same place, we got superposition, it was brighter, okay? Now, what about this one? Imagine for a second what would happen if this bottom one went through a wavelength here, okay? Regardless of where it's starting, at the top, at the bottom, whatever, but let's assume that it goes through a complete wave, right? If that goes through a complete wave during that path difference, right, that means that right here and right there, those two lines are doing the same thing. Those two rays are doing the same thing at the same time, just like they were here, because this one's gone through a whole wave, right? Now, if these two are doing the same thing at the same time, and from this point on, they have the same distance, what are we going to get here? We're going to get a bright spot, right? Again, we're going to get that constructive interference. Now, this is going to continue on and on and on, right? You're going to have another spot over here where you've got some distance, and now this one is a lot farther, right? Getting to the same position. Now, again, there's going to be a place where this line and this line are the same distance from here, right? But what's happening in this first little bit here? If I go through two complete wavelengths, that means that at this point, the bottom line is doing the same thing as the top line, because they were doing the same thing here. Remember, they were coherent, they were in phase, all right? Now, because it went through two complete cycles, then it's in the same place again, right? Even though it's gone through two extra cycles, now it's in the same place again, and now they travel the same distance, and then I get constructive interference, and I get another bright spot there. And so you can see how this is going to happen all the way down the floor, all the way across the wall. Now, what about in the middle, right? What about in the middle? All right. So I'm gonna see if I can erase what we got here. Okay. At least I can get rid of the green. It appears. Let's see. Can I get rid of that blue there? I don't really want to get rid of everything, do I? Oh, there went my coherent light. Okay. So this is fine. So we've got the light that before was going the same distance, right, to get there. I was traveling the same distance right in the middle. I was getting that bright spot. Okay. What if it's not quite? Remember, we had this other one, which was a bright spot because it had a path difference of one wavelength. Okay. What about right in the middle? Okay. What would happen right here if I've got a line going here and a line going there, right? The bottom one is still longer than the top one, but because it's a little bit closer, it's not really a whole wavelength, right? In fact, it might be, see that right there? That right there might be a path difference of half of a wavelength, okay? Now, if the waves are doing exactly the same thing here, and then the bottom one goes through half of a wave, that means that these two lines now have a path difference, or a phase difference of pi, right? The bottom one's gone through a half cycle while this first one is still at its initial point. Okay, now what does this mean? That means that when they travel the same distance, the one here on the bottom is always going to be opposite the one on the top because it has a pi phase change, right? It's exactly opposite because it's gone through half a cycle already. Now, if they're doing the opposite thing at the same time, if the top one is a crest and the bottom is a trough, or if the bottom is a trough and the top is a crest, or anything in between, what's going to happen here? Well, it's going to be complete destructive interference, which means they're going to have a black spot, a dark spot there. All right? So what we expect, because of this constructive destructive interference, is we expect a bright spot, and then a dark spot, and then a bright spot, and then a dark spot, right? And so when we have a path difference, when the path difference is any integer times the wavelength, then I get constructive interference. And if I get constructive interference, I get a bright spot. Anytime the path difference is n times, sorry, not times, n plus 1/2 times lambda, so any integer plus 1/2, it means that I've gone an extra half wavelength somewhere in there. And if one of them has gone an extra half wavelength, then I get destructive interference. All right? Let me see if I can demonstrate in another way, right? Every single one of these, right? Every single one of these points where the path difference, so going from P and Q to the same point, right? If this and this are the same, then all that matters is what's happening here, right? If this is a full wavelength, then that means that this point and this point are doing exactly the same thing at the same time. They're in phase, they're coherent, just like the original light was. Okay, so just like we get a bright spot here because these two are doing the same thing at the same time, sometimes they've constructively interfered a crest and sometimes they've constructively interfered a trough, but that's what makes it bright, right? Is a wave that's even taller and lower than it was before. A wave like this would not be as bright, right? The amplitude has that squared relationship with the intensity, okay? So as long as this is lambda or any integer multiple of lambda, then I'm going to get constructive interference. All right? All right, this is one more way to kind of visualize it. This is going to give us a chance to put together a formula. All right? S here represents the distance between the bright fringes, okay, between those bright marks. So I got a bright mark here at the center, distance between the center of the bright marks, okay. D, you can see, is the distance of the double slits from the wall, okay. So double slit to the wall, okay. The small d is this distance. It's the width of the slits, okay? And lambda, of course, is the wavelength, okay? Of the light, okay? Now, hopefully this drawing is going to help us understand why that is the case. Now something that's going to be important here is something called the small angle approximation. Okay, and this is moderately important because it does come out sometimes in the IB exams. All right, small angle approximation. I want you to, if you have a chance, if you got your calculator in front of you, to try this on your calculator, because the small angle approximation says that if I have an angle in radians, the tangent of that angle is equal to the sine of that angle, okay? Now, if you think of a really long, skinny triangle, that should kind of make sense, that the tangent, the opposite over the adjacent, is almost the same thing as the opposite over the hypotenuse, because these two sides are almost exactly the same if it's a really, really small angle and if this is really, really far away. I mean, you look at this and A and H are almost exactly the same length. H is, yeah, a little bit longer, but the farther this is away and the smaller that angle is, the closer A and H come to being together, to being the same, okay? Now, the other thing that we say with the small angle approximation, this is where I want you to try it on your calculator, is that it's actually also equal to theta. Okay, tangent of theta equals sine of theta equals theta. Try putting a small angle in radians in for theta. Make sure that your calculator's in radians, and then put in something like 0.5. Do tangent of theta, do sine of theta, and then theta, of course, and see what you get. Okay, as long as you have small angles, usually less than, I don't know, about 15 degrees, which half a radian is definitely smaller than that. As long as you use small angles, then these three things should be close. And if you try something smaller, try 0.1. You'll notice that tangent of 0.1, sine of 0.1, and 0.1 are all pretty close together. The smaller it gets, the better the angle, the approximation gets. Now this is important because of what we see here, right? We have this big triangle, okay, in which I've got theta here, and tangent of theta is equal to the opposite over the, sorry, that's not tangent, yeah, opposite over adjacent, right? S is this, and D is the distance from the wall. And then we also have this angle right here, right? Now this angle right here is also theta, okay? If you want, you can go through and try to prove that. You should be able to go through and make that proof by looking at right angles and finding out how things connect and that type of thing. You can show that those two angles are the same. For this angle, here's my right angle. All right, so for this angle, I know that I have constructive interference when this is lambda or a multiple of lambda, okay? And so the first bright spot is going to happen when sine of theta equals the opposite, which is lambda, over the hypotenuse, which is the distance between the two slits, which is d. You're not going to have to be able to prove this during an exam, but I want you to understand the small angle approximation because that idea does come up from time to time during an exam. All right, so because the angle is small, sine of theta equals tangent of theta, and therefore S over D equals lambda over D, okay? And that's exactly the formula that we have there. Now in your formula packet, it's actually S equals lambda D over D, okay? They just multiply both sides by the big D. But I wanted you to see where it came from. But yes, this is in your formula packet. You have to recognize that this gives you the distance between the bright marks, the bright fringes, when you have double angle approximation, the double slit. All right. Now I want you to check out this video. We're going to go in search of a real double slit interference pattern. All right.
All right, guys, we're in for a treat today. We're going to be searching. You can see I've waited until it was quite late. It's just after midnight. This is the best time that we can find one of the most rare creatures, one of the most amazing creatures on this earth, which is the double slit phenomena. We're going to see some double slit interference, but we got to find it first, all right? So follow along with me, okay? We're going to go down into the deepest, darkest part of this building, which is the basement, all right? So we're going to head downstairs. Come on down with me. All right, so we've got to be really quiet. All right, we got to make sure that we're quiet here. We don't want to scare it away. It doesn't happen very often. Okay, you know, the double slit interference, it has to have a light source. It has to have a light source where the laser is coherent. And that's hard to come by, a coherent light source, because that means that the frequency of all the waves leaving the light have to be the same. It's got to be a single color. I think we're okay. The other thing that's hard to come by is that part of being coherent is that the wave is basically doing the same thing at the same time. Like all of the wave is being very consistent in how it's leaving the source. And that's very difficult to come by. All right, so we're gonna keep on sneaking down here, and let's see if we can find it. All right, come on with me. Come on down here. All right. Oh yeah, it's nice and dark in here. I think we got a good chance of finding it. All right, follow me. Come on. I think we're getting close. almost there, all right? Keep coming with me. This is gonna be awesome. I see it. It's right there. It's right there. I can see it. Crikey, it's beautiful. Come with me. Here, I'll show you. We're gonna see if we can get up nice and close, so we can get a better idea of what it looks like. All right, come with me. Can you see it? Can you see it? Here, come on. Slowly, slowly and quietly. Here we go. Oh, look at that beaut. Look at that. It's so odd. It's so beautiful. It's so amazing. Look at that. Oh, I don't think it likes us being that close. Here we go. Okay, you see that? You see that right there? Ooh, must have some kind of defense mechanism. All right, you can get a good look at it now. All right. Now, when you're looking at this, all right, one of the things that you can see is that the lines are all the same distance apart, right? Each of those bright fringes is exactly the same distance apart from the middle of one to the middle of the other. They're all just about the same, all right? The other thing is you'll see they're brighter in the middle. Now, this makes sense, right? It should be brighter in the middle. Okay, you see this right here, right? You see those guys? You see those individual lines. There's bright spots and there's dark spots, right? The bright is where the distance from the two slits is the same, or remember where the path difference is one wavelength, right? Or two wavelengths, an integer wavelength. Anytime you have a path difference of an integer wavelength, you get to see a bright spot because of the constructive interference. Okay, now in the middle of those, you can see spots where it's completely dark, right? And the completely dark is really, really neat because that means there's got to be waves there because of the diffraction, right? When you have diffraction, the light spreads out, right? The light is spreading out like this, and so the waves have to be everywhere. So the fact that you have bright and dark is evidence of this idea of the constructive and destructive interference, right? And it shows that light is definitely a wave because only a wave would have this type of phenomena, which is awesome. All right. Now we're going to see if we can sneak up a little bit closer. Okay. We're going to see if we can find the source over here. All right. So follow along with me. We're going to see if we can get that guy now. All right. Here we go. We're going to sneak up on him. We're almost there. Oh, here we go. Oh yeah. Oh yeah. This guy looks good. This guy looks really good. All right, here we go. He's right here. You see this guy? Where is he? Ah, there he is. See that? I'm gonna see if I can pick him up without him biting me. All right, they can be pretty vicious at times. All right. All right. I got him. There he is. I want you to see that, right? You may or may not be able to see each one of those white lines is actually two lines. There's a black line going right down the middle. And so that's my double slit. I actually have 3 different sized double slits here. All right. And at some point we may take the time to kind of look through that and see what it looks like. All right. But for today, it's just enough to know that I do have a double slit here, and that's what my laser's going through. All right. So hope you were able to kind of see that and get an idea of what it looks like when you have the double slit interference. All right, that was kind of an exciting adventure for us today. All right, I'm going to send you back to your class because it's a little bit safer there.